everyone, thank you so much for joining this video. Here are today's learning objectives. So the first is to understand the terms rate of reaction, rate equation, order with respect to a substance in a rate equation, overall order of reaction, rate constant, half-life, rate determining step, activation energy, and heterogeneous and homogeneous catalyst. The next is to be able to determine and use rate equations of the form rate equals K, concentration of A to the power of M, concentration of B to the power of N, where M and N are 0, 1, or 2. Number 3 is to be able to select and justify a suitable experimental technique to obtain rate data for a given reaction, including titration, calorimetry, mass change, volume of gas evolved, and other suitable techniques for a given reaction. And the last learning objective is to understand experiments that can be used to investigate reaction rates by an initial rate method, so like an iodine clock, or a continuous monitoring method to generate data to enable concentration time or volume time graphs to be plotted. So the definition of order of reaction is the power to which the concentration of the reactant is raised in the rate equation. So if we have rate equals K times the concentration of A to the power of, let's say, 2, that means that the order of reaction in respect to A is 2, and this is because this is the power to which the concentration of A is raised. And then the rate constant, which is K, is a coefficient of proportionality relating the rate of a chemical reaction at a given temperature to the concentrations of the reactants. We're firstly going to recap the definitions for rate of reaction and activation energy. So the rate of reaction is the change in concentration of a reactant or product per unit time. So basically, it's a measure of how fast the reaction takes place. And the definition of activation energy is the minimum amount of energy required for a successful collision. And this varies for different reactions. So by experiment, the rate of a chemical reaction is related to the concentration of reactants by the rate equation of the form rate equals K times by the concentration of A multiplied by M multiplied by the concentration of B to the power of N. So this rate equation is for a chemical equation of the form X amount of A plus Y amount of B goes to form the products. And so what we have is actually that the rate is proportional, directly proportional to the concentration of A to the power of N, where N is equal to 0, 1, or 2. And this power we call the order of reaction. And depending on this order, all the graphs, the relationship between the rate and this concentration will be different. And so because for this XA plus YB forms products, that's why this rate equation is like this, because if we have the rate is directly proportional to A to the power of, let's say, M, and we also have that rate is directly proportional to B, the concentration of B, multiplied by N, then that means we have that the rate is equal to K times this concentration of A to the power of M, and K becomes a rate constant. And we have the same thing for B. So combining these two, we form this rate equation of rate equals K to the power K multiplied by the concentration of A to the power of M multiplied by the concentration of B to the power of N. And M and N and the orders of reaction are determined experimentally, so they can't be theoretically given a value. So for the order of reactions, how we word it is that we say the order of reaction with respect to A is M, and the order of reaction with respect to B is N. And K, which is the rate constant, varies with temperature. So we'll actually come to find that K increases when the temperature increases. And the units of K depend on the order of the reaction. The overall order of reaction we would work out by adding up all the orders of reactions. So we have that the overall order of reaction would be equal to m plus n. Now we're going to quickly go through some definitions that we need to know for this topic. So first is half-life, and this is the amount of time taken for half of the reactant to be used up. And we normally use this term when we look at concentration time graphs, and it's the amount of time taken for half of the concentration of that reactant to be used up. Next is rate determining step, and this is the slowest step in the mechanism of a reaction. So a reaction can be split up. It can either be one step or it can be a couple of steps, and this slowest step determines the rate of reaction. A heterogeneous catalyst is a catalyst which is in a different state as the reactants and products. So it could be a solid whilst the reactants and products are all gases. And a homogeneous catalyst is a catalyst in the same state as the reactants and products. So we can investigate reaction rates by either an initial rates method or a continuous monitoring method. An example of initial rates is the iodine clock reaction, and results are recorded for several reactions starting at different concentrations. So you do one experiment with specific concentrations, and then you would then alter those concentrations and then record some more results. And you would plot a graph of rate over concentration. For the continuous monitoring method, what you do is you measure the rate at several points during one reaction. So we can investigate reaction rates by either an initial rates method or a continuous monitoring method. So the difference is that for initial rates, the results are recorded for several reactions starting at different concentrations. So we do one experiment with specific concentrations, and then we do it again, but with altered concentrations, and then we plot a graph of rate over concentration. However, for the continuous monitoring method, we measure the rate at several points during one reaction, and we do this by measuring the volume of gas produced over the amount of time. And so we obtain a graph of rate over concentration, which is the same as the initial rates. So some ways to obtain rate data are to look at gas produced, the change in mass, use colorimetry or titration, and there's many other ones, but we're going to quickly talk through these. So for gas production, we either measure the volume of or the mass of gas produced and plot a graph of that volume over time, and we find the gradient at the start, and the rate will be proportional to the gradient. Or we time how long it takes to reach a specific point early in the reaction, and the rate will be proportional to the volume or the mass divided by time. An example of this kind of reaction would be when you add magnesium to hydrochloric acid. And then for mass change, you do the same thing. So you measure the mass of gas produced over time, and then you find the gradient at several points through the experiment. So this would be a continuous rates method, and the rate will be proportional to the gradient. For colorimetry, you use a colorimeter to measure the absorbance, so how much light is absorbed at various times during the reaction, and this absorbance will be proportional to the concentration. We then plot a graph of absorbance over time and find the gradient at various points, and so this is also a continuous rates method, and the rate will be proportional to the gradient. For titration, we regularly take samples out at different times and then titrate these samples. So this is again a continuous rates method, and then by titrating we can find its concentration, and we can plot concentration over time and find the gradient to find the rate.